of two vectors x m times 1 y as xy transpose equals, so xy a equals xy transpose. So this thing is hold on. So yes, you can see the screen, or the screen is being updated rather slowly, right, guys? Guys, can say someone say something to tell me whether I'm audible or not?
Yes, sir, you're audible.
Yes, sir. So I was worried since network is playing tricks today. So it might be that you are looking at a blank screen, and so there's some screen lag today. So we define the outer product of two vectors as this, and this A is, as you might see, fine, and x equals x1 xm, y1 yn, then xy transpose equals y1 x2 y1 xm, or no, xy transpose. So x1 y2 x1 yn and xm, right? So this matrix, the elements of this matrix are functions of individual entries of x and y. Fine. The inner product depends on the cumulative behavior of x and y, whereas here the entries of this matrix are individual, or are functions of the individual elements of x and y. So with this, or with the definition of the outer product in our heads, knowing the definition of the outer product defined for a random vector x, the outer product x equals x1 till xn. So the random vector x consists of n entries x1 till xn, and we define the outer product as of x with itself as xx transpose equals x1 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 x2 2. Right. And so this XX transpose is a rank 1 matrix. Any outer product is a rank 1 matrix. Okay, so do I need to prove that, or is it obvious? So I'll say that and write this as a separate outer product is a rank 1 matrix. So is this result obvious, or do I need to prove this? Actually, better. Prove that any outer product is a rank 1 matrix. So right now, you have to take my word that this outer product is a rank 1 matrix, and we define R equals expectation of XX transpose as a correlation matrix. This can possibly be full rank, since this is nothing but, so since in for a, you can see that a continuous X, this will be defined as an integration and in the discrete case this will be a summation, so this can be a full rank matrix. Fine. We also define the matrix. So like the correlation matrix, we also define the covariance matrix. Sigma has expectation of x minus mu transpose, this beast. So this again is, sorry, this should be capital, should be capital x1 minus mu1 whole square, x1 minus mu1, x2 minus mu2, you can fill this up and the expectation sits out here. So this is sigma 1 square, sigma 1 2 as we had defined earlier, sigma 1 3, sigma 1 n, sigma n square. Fine. So this is called the, I repeat, this is called the covariance matrix. This is called covariance matrix of a random vector. Fine. So let me list out some properties of the covariance matrix. So for the first property, fine, 1. Xi minus mu. Sorry, I'll write it like this. Xi minus mu I into xj minus mu j. Is this right? Guys, is this right? Rajesh, is this right? Pavan?
Yes, yes, sir.
Yeah, great. So I take an expectation on both sides. So I'll say that sigma ij, sigma ji, right? So the first property is that the covariance matrix is symmetric. Fine. So the covariance matrix is symmetric. Now, since this is symmetric, we can express this sigma equals p lambda with P being an orthogonal matrix, that is P transpose P equals PP transpose equals, right? So the first property is that this is a symmetric matrix and it can be diagonalized with the diagonalization matrix being orthogonal. So P is orthogonal or orthonormal. First property. The second property is P is positive P is positive semi-indefinite. So what does a positive semi-indefinite matrix mean? Anyone? Gandhi, are you there?
Yes, sir.
Yeah, so do you remember what does a positive semi-indefinite matrix mean?
No, sir.
Huh?
No, sir.
Okay, no problem. So positive semi-indefinite matrix means a positive semi-definite matrix A such that for all x in x transpose so this x transpose Ax will be a scalar PSD matrix. So A is square. A is square n times n. Yeah. So this is a positive semi-definite matrix. This is called positive definite if fine. So all x not equal to 0. Fine. And 3 all the eigenvalues of A of R, sorry, of C sigma are greater than equal to. This is the third property. Fine. So I see that the screen projection is that good. It'll come. I'll hold on till then. It's bad. Screen projection is bad.
Excuse me, sir.
I'll hold on. Yeah, yes.
Sir, if P is a positive semi-definite matrix, then
Yeah.
can we say that sigma is also PSD?
So P, oh sorry, not P, not P. Sigma is PSD. Sigma is PSD. P, sorry. Correct it. Thank you. So now is it okay? Pavan? Pavan asked it, right?
No, sir.
Pavan? Yes, sorry. Yes, so now is it okay?
Yes, sir. I had another doubt, but it's okay now.
Yeah.
I thought that P is
Okay,
also
fine.
PSD.
No, P is not PSD. P is the properties of P go beyond this course. Fine. So all the eigenvalues of sigma are greater than or equal to 0, and actually you can these two properties that all the eigenvalues are greater than or equal to 0 and semi-definite, these are interchangeable most of the time. Most of the time, we state these separately because one does not always directly imply the other, but for most practical purposes, you can treat them as the same. But they are separate things otherwise. So now we define the next thing, complex random vectors. So I hear someone's mind saying, तुमको छोड़ मत देना. पहले कॉम्प्लेक्स किया, फिर वेक्टर बनाया, फिर वेक्टर को भी कॉम्प्लेक्स कर दिया. So now x, the random vector x, is an element of this the n-dimensional complex space. Expectation of x is mu. And since we had the notion of complex conjugates, in while dealing with complex numbers earlier, we will continue that and define the norm of x for complex vectors as x Hermitian x. This equals x conjugate transpose of x. So this operator A Hermitian equals for any matrix A conjugate transpose. So Hermitian, I'll write it out. The Hermitian operator is conjugate transposition. Fine. So now with this knowledge, we define R, the correlation matrix, as expectation of XX Hermitian and the covariance matrix sigma as x minus mu Hermitian. So the first thing that you will notice is that if I take the transpose of this, so if I take the transpose of XX transpose whole transpose equals x transpose x transpose, right, equals XX transpose. Whereas if I take transpose, this is Hermitian transpose x transpose equals x conjugate x transpose. So this is not equal to XX Hermitian. So, but if I take the Hermitian of XX Hermitian, so conjugate of conjugate is the complex number itself. So again, conjugation. So XX Hermitian is XX Hermitian. Therefore, both R and sigma are symmetric under the Hermitian operation and are called Hermitian symmetric. So both R and sigma are Hermitian symmetric. So therefore, sigma Hermitian equals sigma. Similarly, to define a positive semi-definite matrix, we say sigma is PST if x Hermitian sigma x is not equal to 0 for all x. So again, the third property is all the values sorry, all the eigenvalues are either real and complex eigenvalues, if any, exist in conjugate pairs. Fine. So conjugate pairs means if lambda is an eigenvalue of sigma, then lambda conjugate is eigenvalue of. Fine. So if lambda is an eigenvalue of sigma, then lambda conjugate is also an eigenvalue of sigma. Fine. The next thing is if x, or rather I'll say it like this. X is called a Gaussian random vector if each of its elements is a Gaussian random variable, and those the PDF of a Gaussian random vector x with a mean mu and sigma with a mean mu and covariance matrix. Covariance matrix. Covariance matrix sigma is given as fx of x equals They were turned off. So now it's working. So it's given as equals 1 upon pi to the power n sigma exponential of minus Hermitian sigma inverse x minus mu if complex and equals pi n by 2 sigma to the power half half 2 pi. Should be minus half. X minus mu transpose sigma inverse x minus if x is fine. So this is the definition of the this is the definition of the complex Gaussian PDA in n dimensions. This is represented as so in the complex case we write this as x in sigma and x in complex. Yes. Fine. So now the next fun thing. So let x be a random vector with covariance matrix sigma. Then can write sigma equals lambda cube emission. This is the same as diagonalization we discussed earlier. or this is the complex equivalent of diagonalization such that Q Hermitian Q equals Q Hermitian equals identity, and such Q's are unitary matrices. These are called unitary matrices. Fine. So now, with this out of the way, we write or we can also write sigma as Q lambda to the power half Q Hermitian. Lambda is diagonal and we define lambda to the power half as a diagonal matrix whose entries are the square roots of the fine. So we can also write sigma equals Q lambda half Q Hermitian Q Hermitian Q lambda half. Now I can write I as Q Hermitian Q Hermitian Q lambda half Q Hermitian. So if I say this is half, this is also sigma half. So we can write sigma as sigma to the power half whole square, or can define the square root for fine. So we can define the square root of a Hermitian symmetric matrix, as you see, and we can also define sigma to the power minus half as sigma to the power half inverse equals Q lambda half. Now Q inverse equals Q Hermitian, that we know. Therefore, sigma minus half equals Q Hermitian, rather sigma minus half equals Q Hermitian lambda half Q Hermitian. So we take the eigenvalues. We are doing this for real eigenvalues. You can decompose this for complex eigenvalues as well. It comes out as like a similar expression, but we are restricting ourselves to real eigenvalues. So this, and so we can actually define any power. You can do this, or you can try this out. Any power of sigma n is simply q lambda to the power n, q Hermitian, with some trickery, or yes, with some trickery. You can also prove this for you. I'm not leaving this as a homework. I'm just stating this. You can also prove this for complex n. Want not leaving this as a homework. Someone wants to do this, they are welcome to. So now let us define y equals sigma power minus half x. Then and so we also assume that so expectation of y equals mu. This is obvious, but the interesting part is the covariance of y. So expectation of y minus, let me call this mu y. Mu y minus mu y Hermitian equals. So this sigma is a constant. It comes out sigma minus half expectation of x minus mu Hermitian sigma minus half equals, this is sigma minus half equals q lambda half q Hermitian q lambda q Hermitian q lambda minus half q Hermitian equals 0. Sorry, identity. So q lambda, so lambda minus half lambda minus half q Hermitian equals q Hermitian equals identity. So for any matrix with a that has a non-identity covariance matrix, we can define, or for any random so for a random vector having a covariance matrix which is non-identity, we can define a linear transformation that results in a covariance matrix that is identity, or we can use this operation. So if entries of x are not IID, can use this operation to generate an IID random full stop. Fine. So this, and for any omega, last thing, any omega in omega. X of omega is a realization of a fine. X of omega is a realization of a random vector. So the next thing that we will cover are random sequences. But in my plan of the world, this was in the post-midterm syllabus. So random sequences and processes are will be covered post-midterm. So we can be open for discussion. So I'll stop the recording and then we can open discussion.